Every image around us contains patterns, shapes, edges, textures, waiting to be understood. In the world of artificial intelligence and computer vision, teaching machines to recognize even the simplest shapes can reveal powerful truths about how learning really works. In this project, we explore a fascinating question. How can a machine automatically distinguish between a circle and a triangle? It may seem simple, but beneath the surface lies a journey through feature extraction, linear separability, and the foundations of neural networks. Section 1. The Shape Classification Challenge. Before we begin, let's think about how humans classify shapes. We instantly notice the roundness of a circle or the pointed corners of a triangle, but a computer sees none of this. It sees pixels, raw colors, and numbers. So our challenge becomes, how do we turn these shapes into something a machine can learn from? To solve this, we first build a pipeline capable of detecting shapes in an image. After detection, we extract meaningful, numerical features, values that capture the essence of what makes a circle and a triangle a triangle. This is the heart of machine learning, transforming visuals into data that a model can understand. Section 2. Extracting key shape features. To teach a machine the difference between these shapes, we focus on three powerful geometric features. 1. Circularity. Circularity is a mathematical measure that tells us how close a shape is to a perfect circle. It uses the formula 4 pi times area divided by perimeter squared for circles. This value is very close to 1. Triangles, on the other hand, score much lower because they have sharp corners and longer perimeters relative to their area. 2. Perimeter. The perimeter measures the total boundary length of the shape. While both shapes can vary in size, their perimeter to area relationship is different enough for our classifier to learn from. 3. Aspect ratio. Aspect ratio is the width to height proportion of a shape. A perfect circle has a ratio close to 1 to 1, but triangles, especially tall or narrow ones, tend to stretch out, making aspect ratio a useful clue. With these three features combined, we now have a compact numerical signature for every shape. Section 3. What is a perceptron? Now comes the intelligence behind the classification, the perceptron. Invented in 1958 by Frank Rosenblatt, the perceptron is considered the grandfather of all neural networks. It's a simple yet powerful model that mimics the behavior of a neuron. It takes in the features we calculated, circularity, perimeter, and aspect ratio, multiplies them by learned weights, adds a bias term, and produces a final output. The output is binary, circle, or triangle. What makes the perceptron interesting is its ability to learn the right decision boundary between the two classes, but only if that boundary is linear. This leads to an important concept. Section 4. Perceptron training. How the model learns training. A perceptron is an iterative process. Here's how it works. Initialization. The model starts with small or zero weights and bias. Prediction. It calculates a weighted sum of inputs and predicts the class. Comparison. The model checks if its prediction matches the true label. Update rule. If it's wrong, the perceptron adjusts its weights. Weights equals weights plus learning rate times actual minus predicted times inputs. Repetition. This continues until the model classifies all samples correctly or reaches the maximum number of iterations. As training progresses, the perceptron slowly shifts its imaginary line, its decision boundary, until it best separates circles from triangles. This is the moment the machine learns. Section 5. Visualizing the feature space. When we plot the extracted features, such as circularity versus aspect ratio, something beautiful happens. Two distinct clusters appear, one cluster for circles and another for triangles. The perceptron's job is to find the perfect straight line that divides these clusters. This visualization is a powerful reminder that good feature engineering can make classification simple. Whenever the features separate cleanly, even a basic model like the perceptron performs exceptionally well. Section 6. Classification on the original image. After training the model, we apply it back onto the original image. Each detected shape is labeled directly on top of the image, circle or triangle. These overlaid labels provide instant visual feedback. Correct classifications appear clearly, and any misclassifications stand out, helping us quickly evaluate the accuracy and robustness of the system. This completes the full pipeline: image processing, feature extraction, perceptron training, final classification, all working together to produce clean, understandable results.
Now, let's look at the key challenges and limitations of using a perceptron-based approach for shape classification. 1. Linear separability constraint. First, perceptrons can only solve problems where the classes are linearly separable. This means the model works well only when the shapes can be divided by a straight line in feature space. But if the shape distributions overlap, or if the circles and triangles appear too similar or intertwined, the classifier becomes confused. As a result, performance drops significantly. Second, the accuracy of our classification fully depends on the quality of the extracted features. If the input image is noisy, blurred, or has occlusions, the features such as circularity or aspect ratio may become unreliable. Poor preprocessing directly leads to degraded classification results, so high-quality feature extraction is essential for the model to work well. 3. Simple model limitations. Finally, the perceptron itself is a very simple model. It struggles with complex shapes, rotated objects, or any nonlinear patterns. For such scenarios, more advanced models, especially convolutional neural networks, perform much better because they learn features automatically and can handle nonlinear relationships. Therefore, while the perceptron is useful for simple, clean shapes, it is not suitable for real-world complexity. These challenges highlight why perceptrons are effective only for basic problems, and why more advanced models are required as the complexity of the dataset increases. This Python program performs shape classification, circle versus triangle, using computer vision plus machine learning. Preprocessing. The image is loaded, converted to grayscale, blurred, and then converted to a binary, black-white image using adaptive thresholding. Contour detection. All contours in the thresholded image are detected. Small contours are removed based on minimum area. Feature extraction. For each contour, the code extracts key features. Circularity measures how round the shape is. Perimeter, length of the contour. Aspect ratio, width to height ratio of bounding box area, area inside the contour. Vertices count, used to auto-label circles versus triangles. Auto-labeling if polygon approx has 3 vertices, triangle, else circle. Model training. A perceptron classifier is created. Features are scaled using standard scaler. The model is trained to distinguish circle 0 and triangle 1. Prediction plus display. For each detected shape, the model predicts its label. The script prints. Predicted label, circularity perimeter, aspect ratio area. The shape is drawn on the image along with a predicted label. The final result image is displayed using matplotlib. In one line, the code reads an image, extracts shape features from contours, auto-labels them, trains a perceptron model, and finally predicts whether each shape is a circle or triangle. From the result, you can observe how the code identifies circles as circle and triangles as triangle, which are inside the green box. Then, as you can see, the code has extracted the features, such as perception, circularity, perimeter, aspect ratio, and area shapes, with high circularity approximately 0.9 and aspect ratio approximately 1 were correctly classified as circles by both the auto-label and perceptron. Shapes with low circularity approximately 0.57 and aspect ratio between 1.14 and 1.15 were correctly classified as triangles by both methods. The visualization confirms the classification. Each shape is enclosed in a green box with the predicted label above it. In conclusion, both the auto-labeling and the perceptron model correctly identify all shapes as circles or triangles based on their extracted geometric features, and the displayed image visually confirms each prediction.